In March 2020, John had just finished restoring this 60s American car. It's hard to believe these days, but somebody actually drove this to work every morning. I think he was probably the boss.
Hello?
Can you design a ventilator that could be made locally, using locally available parts, and demonstrated in 10 days from now?
Well, I can certainly give it a try.
Well, that would be great.
Yeah, okay, you're on. I'll do it.
We'd better get a move on.
That is roughly what I said in real life, actually.
So, why did we agree to such a crazy challenge? We agreed to do this because we live in South Wales, which has a disposable income 20% lower than the UK national average, while London, for example, is 30% above. The best gear often tends to go where the money is, and it certainly isn't around here.
Money talks, speed walks, sheep bills can't fill the box.
Come on then, let's go for a ride in an ambulance. Look out for the red car. Well, that's one way to get through a 2-hour traffic jam. Here's an oxygen cylinder. This is a vital signs monitor, and here is an ambulance ventilator. Although compact, a big problem with these is that they can empty a large oxygen cylinder very quickly. This is the ventilator on an anesthetic machine, as seen in all good hospital medical dramas. This is an ICU ventilator, which is usually a lot more sophisticated. These are extremely expensive, have hundreds of parts, and consume an enormous amount of oxygen per minute. They're not made in the UK, and that was a big problem early on in COVID. So, what was the problem with ventilators, and why were we so worried back then over what was happening in Italy? An intensive care unit doctor on the front lines at that time will now explain.
My name's Giacomo Tissigli. I'm currently a consultant anaesthetist, but at the time of the pandemic, I was in my penultimate year of anaesthetic training at a hospital major in central London. I've been hearing a bit about the pandemic, so in January there seems to be more and more information about this potential cluster of illness around a wet market in China. That happened a few times and it died down again, so people knew about it but weren't worried about it too much, and if there was one country that was going to potentially control it, the feeling was that would be China. Kind of around Easter time, so kind of early March, lots of people coming back from ski trips and becoming quite unwell. People started to worry a little bit that actually potentially this wasn't contained. And I suppose one of the things around the department that I was in was there were lots of anaesthetists and surgeons who were Italian and actually from North Italy, so had lots of friends in Bergamo, Milan. And very, very quickly it was becoming apparent that this was not contained at all. And we had a pandemic on our hand and it was rapidly escalating out of control. This was kind of before we had any kind of talk of lockdown in the UK, but I sort of felt that this was potentially going to be a true global pandemic.
So this was early March?
This was early March. And so I initially, I remember I've still got the Twitter message I sent to a kind of group of kind of very nerdy anaesthetists and sort of said, guys, I think this is potentially the big one. Should we be kind of forming groups to start building ventilators? And a few people said, no, we're going to have to leave it to the big manufacturers. And then as I was hearing more and more from people who had friends back home in Italy, that of kind of how completely out of control the situation was getting, I actually sat down and wrote an email to the heads of engineering just to say that this really looked like a true kind of global pandemic, sort of end times, one of the ones that kind of disaster movies are made of. That I was sure that there would be a shortage of intensive care ventilators. And so one of the things, I was thinking in the back of my head was actually that we needed a kind of, clean slate approach to try and supplement existing supplies and existing manufacturing efforts.
To understand why they contacted John, we have to go back to the 90s when he was at a conference in Tasmania. He was having a drink with two Australian doctors who wanted to parachute down to a patient with enough gear to provide 24 hours of ICU level care.
Go, go, go!
Including the ventilator and including the oxygen to supply the ventilator. They challenged him to design a very compact, simple ventilator that hardly used any oxygen, but was powered by the gas pressure in the oxygen cylinder. He went home and thought about it, and in the end came up with this machine. It used about 1 litre per minute of oxygen. There are spy films even now where the computer hacker character, for some reason, has a computer that can only put 1 letter at a time on the screen. This is movie nonsense, of course, but it actually comes from 50s computers that didn't have screens at all. They would output the results using a printer. This is a golf ball head teleprinter and is a design classic. It's completely electromechanical, and so as our ventilator is going to be built along similar lines, the titles in this film are going to be done in the same way from now on. Going back to the ventilator then, does it still work? Well, let's find out. The first thing is to get it out of the attic. This machine has not run for 20 years. You can see it's extremely basic in terms of controls. It has no electronics at all. The brain of the device, if you like, is gas-powered. And to test it, we're going to need something called a test lung. This has a right and left silicone bellows to simulate each lung. It also has a windpipe with a left and right airway to each lung. As you can see, our old ventilator does seem to be running a bit fast, but it works. How did it work? Well, high-pressure gas from the oxygen cylinder, shown in dark blue here, pushed a small piston, which in turn pushed a much larger piston back and forth, ventilating the lungs through some valves. It would draw in room air, and the waste oxygen from the brain of the device, which was gas-powered, was then added to this room air. This project was put on the back burner until 2008, when we realized we could also use the small piston to squeeze a resuscitation bag, and we presented this in 2008 at a conference in Denmark. You can see the waste oxygen here in red being added to the air inlet of the bag. We wrote both of these projects up as a report in 2010, with this grand title which included the word pandemic. This, I suspect, is why the phone was ringing off the hook in March 2020. The first step was to put together a team. Since 2008, John had been obsessed with building a skateboard that balanced itself like a Segway scooter, and he finally succeeded in doing this. These are early versions filmed here way before they were commercially available. Meanwhile, Nick, since childhood, had been obsessed with building boats, each version being an improvement on the previous one. When he was 19, he built a Segway scooter and then a one-wheeled motorcycle from scratch. Meanwhile, John's skateboards continued to improve and he started getting into one-wheeled motorcycles as well, simply because they're really cool, fun to ride, and there are some great beaches around here. Just look at that deserted beach. Later on, Nick came to university in Swansea, and so they started collaborating on these designs. This is a later one from around 2019, just before COVID stopped all development. This skateboard was a later design for very soft sand. Nick eventually got into real boats and restored an old one here in Swansea Marina. There's quite a few barnacles on this one. Meanwhile, David Williams, one of John's work colleagues, became the other member of the team and the software guy. Here's an earlier medical project they worked on together. It's a gesture-controlled ultrasound machine, so you don't de-sterilize your gloves when you're operating it. This one is a wearable vital signs display, a kind of low-cost Google Glass, if you like. And this is the view you get when looking through it. So between us, we had a lot of equipment. We have motors. We had small computers for embedding in these machines. We had various types of rechargeable batteries. All sorts of small displays that were commonly available to hobbyists. And also a workshop to build this ventilator in when the lockdowns hit. We also had enough experience between us all building things to actually construct something that might work. What do I mean here by the words reality check? Well, parts for just about everything in the world are made in China these days, and they come on container ships. However, their supply chain had totally failed. So this ventilator is going to have to be made using local materials and local engineering skills. One requirement from the UK guidelines published for these ventilators was that they should have an oxygen consumption less than 3 liters a minute.
Can't always have what you want.
So this completely ruled out all conventional ICU ventilator designs, even if they could be built, as they tend to use way more oxygen than this. It was just not going to happen. These new ventilators were going to look completely different from anything clinicians were used to using. Are there any historic precedents for this kind of approach? Well, in Cuba, for example, it's well known they keep 50s American cars running using extremely creative engineering. And there's even an instruction manual on how to improvise and build designs from anything they had available. Lockheed in the US built their first fighter jet in 1943 in 20 weeks and is an example of what can be done when all red tape is removed. How bad could things get? Well, clearly not that bad, but remember, by the first week, people were fighting over toilet rolls in the supermarket. In our imaginary Mad Max post-apocalypse hospital, therefore, will we have any oxygen? And if we do, will it be under pressure? Will we have any electrical power? Will there be any staff, or will they have all run away? Let's look at oxygen then to begin with. Oxygen is made by freezing air until it liquefies. It's delivered as a liquid to large thermos flask-type storage tanks, and these have a radiator on the side that draws heat from the environment to turn the liquid back into gas form. Now, this one was filmed in Eastern Europe during COVID, and this is ice, condensed water from the air surrounding the radiator, and I suspect its function was seriously impaired. But if the gas does make it to the hospital ward, it comes in through wall connectors at 4 times atmospheric pressure as an oxygen line and an air line. What about electrical power? Well, the UK still has a bit of an oil industry in the North Sea, so it's reasonable to assume that hospitals would have power, or at least some fuel for their generators. And it's reasonable to assume electricity would be available for our ventilator, therefore. What about staff to run these ventilators? Would they all run away? Well, John had once seen a lecture by a junior doctor who was present during the Chinese SARS outbreak in 2002, and at that time she'd been a middle-grade doctor on a baby intensive care unit, as she was training to be a pediatrician. During SARS, she found herself as the most senior person on an adult intensive care unit because all the consultants had run away to the countryside. They worked 12-hour shifts wearing spacesuits, faxing messages back and forth because the windows and doors had been taped shut. So, normal society could break down. In our post-apocalypse hospital, we thought we would have oxygen shortages with reduced flow and reduced pressures. Power probably would be okay, and as for staff, we just didn't know. Would everybody run away? Nobody knew. As things unfolded, certainly for oxygen, there were serious shortages of oxygen in UK hospitals early on, and doctors were being asked to limit the number of people put on ventilators and CPAP. To illustrate some of these problems, this is an oxygen market and refilling station in India, and it takes a lot of skill to roll a cylinder like that, especially if you're wearing flimsy shoes. Here is the queue of people outside trying to buy oxygen for family members in hospital. A little medical moment now, so bear with me. Why do we have lungs anyway? What do they do? Well, the airways of the lungs are like the branches of a tree, getting smaller and smaller, and at the ends of each branch you'll find little clusters of air sacs called alveoli with blood vessels that run all around them. Their job is to allow oxygen to move from the air onto the red blood cells flowing by, and carbon dioxide, a waste product, to be breathed out. Now, listen carefully. Listen for that. Doesn't sound good, does it? If these alveoli are full of blood and fluid and infection, then this gas exchange doesn't take place very well. And that's the problem you had during COVID. While we're in that part of the body, why do we have a heart, which is next to the lungs? It's pumping the red blood cells to all the cells of the body, carrying the oxygen to them. So, what exactly is a ventilator? To answer that, we need to go back into history.
This is one of my most favourite places on the planet, which is also fairly near to where I live. Now listen for it.
Check for pulse. Analyzing now. Stand clear. No shock advised.
In the late 1700s, this would not have been a defibrillator. This would have been a rescue set for drowning or near drowning.
Drowning and near drowning was very common hundreds of years ago, and most sailors didn't know how to swim. It was almost considered unlucky. Also, the concept of inflating bellows was well known. They were used in blacksmith forges. In medieval times, midwives amongst the poorer people were known to blow into the mouths of babies to stimulate the first breath. Although this was considered extremely vulgar, resuscitation kits did appear, but you will notice there's no face mask. Now, why might that be? Well, I'll explain. One clue is that the New World had been discovered and tobacco-based medical treatments were all the rage at this time, including the smoke rescue kit, shown in operation here. One treatment for near drowning that might have worked a little better was rolling the patient over a barrel, as being demonstrated here. And another way was to put them across a trotting horse, or in this case an ox. I'm not sure if this guy's drowned or just been drinking too much. By the 1800s, the concept of inflating the lungs with a bellows made an appearance, although it was considered extremely risky and dangerous. Which is true if you don't know what you're doing. Polio outbreaks in the 1950s changed everything. It affected the nervous system so your lungs were okay, but you just couldn't breathe in or out. One treatment in terms of ventilation was the so-called iron lungs. The pressure inside the box was increased and decreased, and in fact they measured it with a U-tube full of water, which you can still buy. The pressure here is 6 centimeters of water, and even on modern ventilators the pressure being applied to the lungs is still measured using these units. So here's the U-tube on the side of the iron lung with the water in it. The patient looks seriously uncomfortable here, and that really will chafe. Nursing care was also a bit of a nightmare because if you opened the hatch, you would lose the ventilation, so you could only give nursing care in really short bursts before the patient suffocated, basically. You could also wheel the patient out to provide nursing care like this, but again, you've lost the ventilation, so presumably you had to be really quick. This is not the Flash Gordon spacesuit, it's actually an attempt to encase just the chest of the patient in the iron lung, while leaving most of their body exposed to the normal environment. Variations of this still exist now for certain use cases. What about modern intensive care ventilation via a tube? That's what we all think of really, isn't it? In 1952, there was a polio epidemic in Denmark, and Diaphragm Hospital only had a handful of iron lungs. A young anaesthetist, Bjorn Ibsen, had just returned from a year in the US. In that time, he'd read of a device made by a US engineer that assisted the breathing of people already in iron lungs through a tracheostomy tube in the front of the neck, and this worked with the iron lung. He'd also assisted the breathing of patients having surgery by squeezing a rubber bag attached to a face mask. It must be remembered that at this time, inflation of the lungs using a bag or bellows was considered somewhat risky. Confronted with a 12-year-old girl, Vivi Ebert, gasping for air in Diaphragm Hospital, he proposed the radical step of ventilating her with a rubber bag via a tracheostomy tube in the front of the neck. Everybody expected this to fail, and they all left the room, but he was actually successful and she recovered. As a result of this, during the outbreak, 1,500 medical students were organized into relays bagging patients manually in 8-hour shifts, with smoke breaks every hour. The chief of the hospital stated that it avoids the dreadful situation of having to choose who to ventilate, in other words. The mortality fell from 87% to 26%. What was the aftermath of all this? Well, the hospital chief published a research paper on this new treatment in his name only. By the time of the 1953 outbreak in Stockholm, early ventilators had started to appear, such as this one. In 1953, Ibsen set up what would now be thought of as the world's first intensive care unit, notably in a different hospital. What do you find in an ICU? Well, here's a view from the end of the bed. You'll find a ventilator of some sort, a vital signs monitor, gas supply lines, usually at 4 times atmospheric pressure, syringe pumps giving drugs such as sedation, fluid management machines, and usually some form of ripple mattress to prevent bed sore formation. Here's a patient being ventilated through a tube into the windpipe, and I've mocked up the windpipe and the left and right branches that go into the lungs for you. You can see that the tube has a very soft cuff on the end, and when it's inserted under a short anesthetic and blown up, it forms an airtight seal, so you can now ventilate the lungs. Here we have a variation where we're ventilating through a tracheostomy. That's a hole into the windpipe through the front of the neck. Now this sounds barbaric, but actually it's far more comfortable for the patient because they're not coughing or choking on a tube that's going through their mouth. And again, this has a cuff which seals and allows them to be ventilated. What about all those resuscitation bag squeezer machines that appeared during COVID? Well, of course, yeah, we built one in 2008. It's not suitable for COVID patients, though. It might be okay for polio, where you have more or less normal lungs. But in COVID, the lungs are diseased, so it's a totally different ballgame. Just for fun, we've rebuilt it for you as most of the parts are still around. And as you can see, again, this one still works. It's a shame, but it just really wasn't good enough for COVID patients. You can see it's connected to our test lung and it's running okay. You can vary the inspiratory time and the time allowed for expiration by turning these little knobs. This is the true story of Fu Xiaopeng, I hope I pronounced that correctly. 20-something years old, paralyzed from the neck down in a motorbike crash. He was hand ventilated by his parents day and night for 7 years using a resuscitation bag until someone in the village made him a ventilator for $32. They could only afford to use it at night. Now we can't get permission to show you photos of that machine, so let's go one better and rebuild it in the workshop. This is an electric wheelchair motor, but otherwise it's the same design. You remember this machine was built for $32 and it worked, but also remember that this man had normal lungs, rather like a polio patient. So it wouldn't be suitable for COVID. Nevertheless, it's still an amazing story that his parents managed to ventilate him for several years by hand. This sliding bearing is a modern component. I think the equivalent they used was actually much more primitive than this. It's woodwork, metalwork, and some creativity, basically. If this reminds you of a railway locomotive wheel drive system, then you are getting close to how this works. The final step of the build is to mount the resuscitation bag on the wall. In his case, they mounted it using elastic bands. If you don't have an on-off switch, you can actually make one like this. And here we go. It's going a bit fast, but this is how it worked. This was the principle. It's a bag squeezing machine, and it was mounted alongside the bed of this young lad. Why would it be a problem ventilating someone with COVID using a resuscitation bag? Well, several reasons, but certainly with the bag we actually tested, the valve that flips from inspiration to expiration would change over prematurely. So here we want to hold the breath, we want to hold the lungs inflated just for a short while before releasing it, but it flips to expiration immediately. This isn't so good when you're trying to ventilate somebody with diseased lungs. Time for a quick break, I think. That coffee looks nice. But wait, I hear you say, can you make a ventilator from a food mixer? Let's find out. This design appeared on the internet during COVID, and just for your delight, we're going to rebuild it for you. The first step is to take a food mixer from the kitchen and then chop off all the parts that we don't need. You can see it's quite a well thought out design. There's an electric motor. There's a gearbox that reduces the speed. All these things are good and provided for us ready-made. We do need a little bit of modification though. Trying hard not to chop off any fingers here. This is the key to the design. A good supply of bearings like these are skateboard wheels. So we reassemble it all and here you go. Now is this crazy or not? Well, obviously it's a bit crazy, but the bag stays put, it doesn't move around, it comes with a speed control built in, and there's a reducing gearbox. So it's kind of crazy, and yet it's not. In our new updated design, what do we need to control? Well, we'll need to control how long it takes for the lungs to be inflated, how long we want to hold the pressure for in the lungs, and how long the period of expiration is as the patient breathes out. And at the end of that, we want a little bit of pressure to stay in the lungs, and I'll explain why later. Here you can see that the pressure being given is 24 centimeters of water over 3 centimeters of water. So when the patient breathes out, the pressure in the lungs doesn't drop to 0, it drops to 3. And there's a reason for that. This is deliberate. Also, if you look at the pressure waveform in yellow at the top, you can see that the top of it is flat, because they're holding the pressure just for a short while before the patient is allowed to breathe out. This is a necessary feature for a COVID ventilator. Here we are ventilating the test lung again. You'll see that the scale is in centimeters of water, and you'll see that we're achieving a pressure of 30, and then it's dropping to 0. Now, we don't want it to drop to 0, that's not good, and I'll now explain why. We've built a model lung view here. Here are the alveoli made from a children's toy. And listen really carefully now. Do you hear that? That horrible sticking sound as the alveoli stick together at the end of each breath is really damaging for them. So what we need to do is when we let the patient breathe out, we leave a little bit of pressure behind, and this is called positive end expiratory pressure, otherwise known as PEEP. Here we're giving a pressure of about 30 over 8. So the peak pressure is 30, and when the patient breathes out, it's 8. It's not 0. So the PEEP here is 8, and those alveoli look a lot happier to me. We need a thing called a PEEP valve. Now these are commercially available, but you just could not get them during COVID. It looks simple, but it's not. If you blow through it slowly, the pressure is 10 on this particular one. But if you blow through it quickly, it's also 10. It doesn't go any higher. So it's 10 regardless of the gas flow rate. It's way more complicated a thing to design correctly than you might at first think. If you take it apart, they vary a little, but they're all fairly similar to this. There's usually a long but very fine spring, and often there's a second spring that's also tapered. So there's a lot going on in there. With the PEEP valve added now, we're putting gas in through the clear hose and then releasing it through the blue hose out through the PEEP valve. And you can see the PEEP is now around 10, 8 to 10, so it's doing its job. It's a shame you couldn't get hold of these valves during COVID. What controls are we going to have on our ventilator? Well, here's 4 knobs that all go to 11. We're going to control the inspiratory time, how long we hold it for, known as the plateau phase, and how long the expiratory time is. Also, we need to control that PEEP pressure somehow or other. Are there any older ventilator designs we might take inspiration from, particularly for harsh environments? Well, if you were posted to this hospital after an apocalypse, a good machine to take would be one of these. This is the first ventilator John ever used as a very junior anaesthetist. It was built in the 1950s and used right up until the 80s. You can see how it works. A cam lifts the weight up and down, which squeezes a bellows. It's rather like an upside-down version of the blender ventilator. You changed speed by changing these units, and it actually has a 3-speed bicycle gearbox as found on the rally chopper bicycles. This video is sent from a museum in Australia. If there's no power, you can connect it to a car battery. And if there's no car battery, you can designate the most junior person in the room to turn the handle. So, it's a proper post-apocalypse ventilator, isn't it? Here we go. The first thing we've got is a humidifier, a bit like the bubble chamber seen in those old Blackdam hospital photos, but updated. And also we have a thing called a mechanical thumb, which blocks the exhale hose, while we put some gas in through the inspiration hose to inflate the lungs. We need to control how long that takes and what the volume is. We then take our thumb off and let the patient breathe out. But remember, we're going to have to provide some PEEP to stop those little alveoli collapsing like they are doing here. We put our thumb on the exhale hose and we push gas into the lungs. So we could do it like this, with gas flowing down one hose, and I'm just using my thumb to regulate the flow to the lungs. But we would have to know the gas flow rate to know the size of each breath. To measure flow rate, you put a restriction in a tube and you measure the pressure difference across it. Here's a demonstration version for you, made using some of this wine. Here's my slight restriction in the tube, and you can see that when we blow gas through this tube, a pressure difference develops across it. If you measure that electronically, then you can measure the flow rate and work out the volume of each breath. This is a commercially available flow sensor used in ventilators, but you couldn't get them during COVID. Some people even started to try and 3D print them. We thought of doing it a completely different way. What about using a giant syringe to inflate the lungs? If you varied the amount of movement of the syringe plunger, then you would know the volume of each breath. The reason we're squirting junior doctors here with a water pistol is because if you take it apart, you'll find there's a mechanism inside that's very similar to what we want to do. There's a one-way valve on the outlet, there's one on the inlet, and there's a plunger, which is a bit like a small syringe. So there are valves, and there's the little plunger. We could copy this on a larger scale, in which case we're going to need an inlet valve, an outlet valve, and a great big syringe. Here are some check valves of various types, including 3D printed, and this is the one we're going to use. You can see how it works. So what about drawing in air with a little bit of oxygen with a syringe? We draw it in, and then we give it to the lungs. Then we release the gas from the lungs with the thumb. Deliver it to the lungs, release. Deliver it to the lungs, exhale using my thumb. By altering how much the syringe moves, we can alter the size of each breath. And crucially, we don't need to have a flow sensor to measure the size of each breath, because these were unavailable during COVID. So this is a way around that major problem. We need to finally consider how we provide oxygen to the inlet of this syringe, and the easiest way is an open-ended reservoir tube. If we set up an oxygen flow into this tube from any source of oxygen at any pressure, it acts as a reservoir, so when it's drawn into the syringe, it's followed by air from the room, which also contains a small amount of oxygen. So this system overall is very oxygen efficient. Therefore, this was the design plan for our ventilator. Instead of a syringe piston which could develop a leak at the seal, we decided to use a bellows which is less likely to do that, and it has one-way valves, an inlet and an outlet. We have some sort of motor and gearbox system that drives the bellows back and forth, by varying amounts, so we can control the size of each breath. There's a power controller to that motor, and then there's a small built-in computer which tells the power controller how far to move the bellows, and in what direction, and at what speed. There's a control panel, there's a display. We need to be able to run this from the mains, but also we need to run it at a lower voltage because a backup battery was one of the requirements. On the exhalation or breathing out side of things, we're now going to fit an electronic thumb, if you like, to replace my own actual thumb in the previous demonstrations, and then the gas from that will go straight out through a PEEP valve, which we've yet to develop. Now you might think, why not just get an on-off, open-close electronic valve and stick it in there as the electronic thumb? Well, the reason for that is that everything on the exhalation side, of course, is dirty gas, contaminated from the lungs. So this equipment has to be sterilizable on that side, or cheap and disposable, one or the other. Other design considerations came upon us as the project went on. The MHRA started asking for extra features. It should be waterproof. You should be able to knock it over onto the floor. We really did wonder at one point if they really wanted ventilators or not.
Nice man has brought me a bellows unit. So what's this? This is an old ventilator from the 1980s. I used it as a trainee, this very one. It's almost indestructible. So you're looking at it thinking there's no way we can build that in the time, but actually forget about all most of it. All we're looking at is the principle. There's a bellows which is pushed back and forth. That's all it's got to do. But it has to be pushed certainly in to the lungs at a rate that's controllable. It's powered by an electric motor. You shouldn't laugh at this kind of technology. It's been used quite successfully in the past.
Here's a ventilator with an internal bellows from the early 2000s. And here is what the one we're taking apart would have looked like.
So it pushes a bellows in and out. Everything else is superfluous, and we will take it off this machine. It makes a good test bed, and that's why we're using it. Bellows can be made in Wales, but they will be made of silicone rubber probably these days. Right, today we're going metric. So I should measure what that should cover everything, I would have thought. Let's go upstairs again. Warp core.
This was our actual design plan for the construction in 10 days of a ventilator. We decided to take an old ventilator that we already had that contained a motor and a bellows, and we would remove all the electronic control systems from it. We would then make a new control system with a computer and electronics, a screen and so on, and use it to try and make it work again. That would then develop the control side of things, and at the same time, in parallel, Nick would design the new frame, a new drive mechanism, and the design of the panels from which it would be made. And the idea was then to mate these two parts together, the new control system and Nick's new mechanical system, at the end, and hopefully we would then have a working ventilator in the shortest possible time.
This is not the final control panel. This is a general purpose test rig. We've got basically a computer. This will tell the power controller how much power to send to the motor in the forward and reverse directions. We're trying to build a ventilator that can be made in large numbers. These are very commonplace. Lots of hobbyists use them, and there's alternatives that also work. They have very high contrast. You can read them in even in brightly lit conditions. This is the 3D printed display holder. The display is going to go in there. It'll slide in the side there. This is looking okay. It's good enough. I'm going to use exactly the same wiring diagram and pins in the interest of saving time, because I'm familiar with it. Here's the charger. This is sort of Chinese electric bike charger. One source of 24 volt backup batteries would be electric bike packs. Another would be higher end, more modern mobility scooters. Okay, turn the power on. So when I turn it on, it should just slowly move, going on now. And stop, go the other way. It's reversing direction and it goes the other way. So we've got control. We're now on day 4. Hang on, here we go, letting go. Right, it always goes back to the start point and then it starts to run. So here's the mini design studio, here we are. So this is the sort of thing we're looking at for the proper mechanism. Very available motor, made in China, and it's used in children's scooters. This is just a 3D printed test piece, okay, and this is a proposed mechanism to move it back and forth.
So, potentially, could the government commandeer all these key parts? Well, it's possible this was our line of thinking, actually. After all, civilian cars were commandeered for the war effort in World War II, and it's well known that iron railings were removed to make steel. Here are some locally that have never been replaced. You can see where the holes have been filled in with cement.
If for any reason the piston moves too far, instead of grinding the whole mechanism to pieces, it actually self-stalls at one end. It would never normally do that in normal operation. It's there for safety, and it's the same at the other end. It's what, I don't know, 9 o'clock. Boris Johnson's just announced lockdown for the UK. We've got limit switches here. This one, by moving it, will set the tidal volume. This is the airway pressure sensor. It's working. The laptop is just to program this computer with and debug it. It will run without the laptop. Although the screen's small, it's very readable. It's not bad. Went to see Hans Science, if I've pronounced that right, at the engineering school, Swansea University, of international reputation. He's taken the bellows out of this and he's going to re-engineer them, 3D print them in rubber, which sounds rather impressive. I'd like to see that happening, but I haven't got time.
Let's take a drive to Barnstaple and meet someone who actually makes ventilators for a living.
We produce equipment almost entirely for low resource areas of the world where oxygen is short, power supplies are bad.
So how did you get started? What was the catalyst for this?
Conversation with an anaesthetist that said, what's the matter with engineers? Why can't they build kit that works in Africa? And that was pretty much where it started.
No, I've seen photographs of hospitals in Africa with modern equipment just rotting outside because it's being donated
or bought, and the small part fails, and then this whole £30,000 machine is effectively junk. The majority of donations to low resource areas of the world are inappropriate. Even WHO state that about 70% of equipment that's donated fails to work. And that's because the conditions are very much different. If I talk to an anaesthetist in the UK and ask them where oxygen comes from, they said, well, it comes out the wall and it's free and as much as you want. And that is not the condition in low resources. They need to be designed so that the equipment isn't dead on arrival. Some years ago, I was fairly appalled that patients were surviving surgery, long and complex surgery, but then they were taken straight off the ventilator and sent back to the ward, and they were losing patients post-operatively. So I decided to build a ventilator that looked and felt like the ventilator on an anaesthetic machine, but was still robust, still efficient with its use of oxygen. As ICUs developed in low-income countries, it was starting to be used for much longer-term ventilation. But whereas most ventilators use huge amounts of pressurised gases, this uses very little. There were certainly reports of hospitals running out and being close to running out early on. Yeah, hospitals in the UK were getting short of oxygen. At one point we did supply oxygen concentrators to an NHS hospital that was getting very, very short. My staff here, some of them had some very difficult conversations with members of the public. We were getting people ringing up and saying, please, can I buy an oxygen concentrator from you? And that was quite difficult for some of the staff to take. Were you being offered silly money? We were, and no, we didn't take it. I was offered a number of ridiculous deals, but through the whole of the pandemic, we never changed our prices at all. And people making profit out of selling more product is fine. People profiteering because of a shortage of product, I really couldn't stand. For a start, I noticed that yours has knobs and buttons, which in a pandemic seems to me perfectly reasonable. I'm sort of old school, or some would say just old, but a nice switch that you can switch without digital controls, certainly in the environments that we work in, is just so much more reliable. Most ventilators will quite easily consume 50 litres a minute. This will use 1 litre a minute. So it's run from oxygen, but then after we've used the oxygen to run the ventilator, we recover the oxygen and give it to the patient. I spoke to somebody from a military anaesthetist who said they were trying to do fairly long retrievals by helicopter. He said, we just can't get enough oxygen cylinders on the aircraft to get to the other end using a conventional ventilator. And when he asked me how many we'd need for this, I said, well, one E-size cylinder, 680 litres, we'll probably run it for 10 hours. So with your hands, just show me how long that cylinder would be. E-size. E-size is about that sort of length, I suppose. Did somebody phone you up, or did you watch this on the television? We saw it on the television. We went to the government's website where you could put in information if you had anything to do with ventilators, which we did. Unfortunately, we didn't receive any response. I contacted our local MP. She gave me the same information. I tried again, and we still got no response. There's a common story. But the thing is, there aren't many ventilator companies in the UK, are there? And the ventilator is registered with the MHRA. So how many ventilator companies are there in the UK? Maybe less than 10? Oh, much less than 10, probably less than 5. We're certainly a small company, a very small company, but we do make ventilators. The first we heard was from a consultancy in Cambridge, Team Consulting, and they contacted us because they found us on Google. My wife and I drove to Cambridge to talk to them. First time I've driven up the M4 with no traffic on it, which was really very odd. And through them, we were then contacted by the UK government. Right, and did they ask
you to make a few?
Initially they asked if we could build a completely unrealistic number of them in very short order, and we're a small company. That really isn't something that we could do. So we made the offer to provide the drawings, the software, the bill of materials, everything you would need to build this ventilator, and then the government could find larger organisations in the UK that could develop that.
Did that then happen?
It did. There was a company in Scotland and another one in England that took on building this. I think both those organisations received contracts with the UK government to build anything around 10,000 apiece, I think.
Those contracts are now publicly available?
They are publicly available, yeah.
Right. I may go and have a look at those at some point.
If we were going to need these sort of ventilators, we've all got relatives, we've all concerned about our own health as well. And I just wanted to get them built. It came to the point where I think the government realised they did not need the number of ventilators they were asking people to produce. The demands for ventilation with patients with COVID dropped considerably, particularly in Africa. I think they did much better through the COVID pandemic in many places than we did. I spoke to somebody from Senegal and I said, have you got any secret tips here? And he said, we're used to dealing with pandemics. And we're used to dealing with disease. He said, and there are 3 golden rules. You go fast, you go hard, and you keep the rules simple. And I think that's a lesson that we could all learn from.
Do you think it helped people being able to actually come to work and do something useful rather than just watch the whole of streaming television?
Absolutely, yeah. And people worked all hours and we just, really knuckled down and got on with things. It was a very difficult time. I mean, everybody was stressed and we were very concerned about, particularly about colleagues we knew overseas that were, they had no PPE. There wasn't shortages, they just didn't have any. We lost a number of good friends and colleagues overseas. I found it quite ironic, really, because during the COVID pandemic in high-income countries, they were short of oxygen, short of equipment, and short of trained personnel. That's our normal environment that we sell into, all those things.
There were certain things, just getting a bit technical, which seemed odd to me, like the taper-fit connectors for the hoses. It was specified they had to be metal. If they were made of Delwyn, which is this black plastic, to me that seems absolutely fine. It
needed a good value analysis from an engineering perspective on what they were doing. And I think you need both clinical expertise and engineering expertise to do that. And in particular, medical expertise that was used to dealing with those sort of shortages. So anaesthetists and intensivists that had experience working in low resource centres, in my opinion, were worth their weight in gold during the pandemic. One of the early conversations with somebody from the government was talking about, needing 30,000 ventilators. I'd said, who's going to run them? And where are you going to get the oxygen to drive them? None of those things would have been available. And building extra hospitals is fine, but you still need staff to man them. So I think there needed to be a little more realism on that. The first specification that they came out with was very appropriate for what they thought was needed. But clinically speaking, the treatment of COVID patients changed, and as it changed, the government changed the specification of what they wanted. Well, that's very difficult to do if you're trying to rapidly produce something. There was a lot of pressure from government to produce at any cost, but there were restrictions on that, some of them extremely valid from people like the MHRA that wanted to ensure equipment was safe. And I can see both ends of that argument, and I think there had to be something in the happy medium in between. But if we'd have needed those 30,000 ventilators in that sort of period, they would have been basic ventilators. Worldwide, we need to recognise the starts of a new pandemic much quicker. We were pretty slow as a world off the mark with that. The government went in a slightly strange direction, trying to get anybody with any sort of, even people with no understanding of the clinical requirements of a ventilator to try and build ventilators. If they'd have focused on the people that did already manufacture ventilators, which in effect is what happened in the end, most of the ventilators that were supplied by people who already made them.
Frantic designing.
Yeah, I'm filming you.
Even easy to make. This is panel construction. So this would be a flat panel, and then this would be a flat panel, and then there'd be a tray down here as well for the electronics. As you can see in this one.
Oh, that's
tray at the bottom.
That's nice. Yep. So that's just what, folded aluminium.
Just folded aluminium. Yeah.
What am I doing? Paperwork. These are the specifications for rapidly developed manufacture ventilator for the crisis we're in. It's by the MHRA, which is the UK equivalent of the FDA. And underneath every question in red, we specify whether we can meet the requirement or not.
Were there any crazy moments?
One of the strangest moments was when a guy turned up at the doorstep here and said he was from the Health and Safety Executive and he needed to come in and inspect the premises. I said, "You're not coming in. I've got this place secure and you're not going to ruin it." In fact, he was a local debt collector that the local council employed to check on companies. They had no knowledge of what biosecurity at all, and I had this place locked down. And he threatened me with prosecution, and I said, "I'm sorry, go ahead, you're not doing it, you're not coming in."
There was a song in the 90s.
Your name's not down, you're not coming in.
For a nightclub. Yeah. Overall, it probably brought out the best in people, would you say?
Yeah.
Maybe the odd exception.
With the odd exception, possibly, yeah.
It's now day, I can't remember, are we at 8, 7, 1:30 in the morning? We went to a guy I've known for a long time, but I haven't seen him for a while, Richard Thomas. And if you want to know anything about metalworking, he's the guy to see. We had a problem with this metal bar. It's salvaged from some old piece of machinery. We tried to cut it in the lathe here, using a tungsten cutting bit. Yeah, a tungsten carbide bit. It's still bounced off. So what we needed to do was anneal the metal to make it softer. We got in touch with Richard. He's got a ray burn in which he burns Welsh anthracite coal, which burns at about 1100 degrees. What are we doing here, Nick? Or Rich?
We're normalising hardened steel rods to be able to work them and put the necessary chamfers and threads into them.
Excellent, because the problem was we put this in a lathe and it just bounced off, but we need the ends softened so we can put screw threads in them. So the way to do that is go to Rich's house in the middle of the night. How do you know if it's annealed, Rich?
This hardened steel?
Yes.
Put the file on it.
That's a file.
Slides off.
Yeah.
Creates a little scratch in.
Yeah.
Nothing there.
Yeah.
Press a little harder. Not that you should put much pressure on the file. Nothing. Not even a scratch.
Right.
Anneal the steel, and now you can hear the difference.
Yeah.
As opposed to.
Yeah.
So that's actually taking material off, and that's actually just sliding across the surface.
Magic. Here ends today's lesson. Back at the shop, we've got these rods, and it just occurs to me, I gave Rich some old RAF aircraft parts, as you do. If the apocalypse happens, we'll end up with a barter economy anyway, won't we? So might as well get used to it, perhaps.
Oh, it's lovely and soft. Lovely and soft.
Is that just any old oil? Or?
Well, this is oil from your car.
Oh, 6 bolt. Go on then, let's see it. Excellent. So that the ends bolt to the metal rods. Basically, that's how the whole thing's held together. Right, we're at Richie's house. This is in Craighkeven Park. Craighkeven Park is famous place because in the war, Grindel Matthews lived on the mountaintop and he invented the death ray. The death ray. It might have been a hoax just to scare the Germans away, but whatever. He had a lab up here and on top of this mountain.
We're taking a trip to Death Ray Mountain, where the lost souls gather around underneath that fountain.
NHS workers by joining it with a mass round of applause, mass round of applause, mass round of applause.
All of our features will be based on this spacing running down the centre line.
You know, on these car shows where there's 5 million things to do and only one night left before the big reveal.
Loud and furious, delirious, loud and furious, desperate, mysterious.
Will they get it started in time for the show?
And it's all kind of stage managed by the producer. Well, in this case, it is real. There's a load of things to do. We're not faking it. Nick is frantically designing more parts. Right, this is all going to be colour coded soon. The requirement of the MHRA specification is that the knobs should be large and easy to turn with gloved hands, double gloved hands. So that's exactly what you've got. For the umpteenth time, I'm unsoldering this screen and getting it ready for our new beautiful cable wiring loom that Nick's made up, all colour coded. Soldered up. Right, so we're going to load my test software, see if these buttons and things do anything. Ready for when Dave comes tonight with some software for this thing. Dave is our kind of a hidden partner because he's been hiding away coding for hours and days. So we're testing Dave's code.
It's waiting. That's what it's meant to do.
That was the RAM. Yeah, the pause.
Yeah,
the hold.
Now, if you wanted to get a different display, you press.
Can I do that?
Press the push button. Yeah.
Ah, right. So what's that saying?
So that now gives you the time of the different
so the total
parameters. It does actually plot a graph, a real-time graph of pressure against time.
Oh, epic. Sake. Early in the morning. One of the MHRA requirements for this machine is that it should have a stand. So some friends in Bristol found me a stand. Just arrived today.
They've also found me oxygen analyzers. One of the requirements is an oxygen analyzer. Dung. The postman just came. For God's sake. We shall now do the unwrapping and see what presents we've been given. Also, the bellows are coming today. The rubber ones. The metal ones might come today, which I really hope they do. The other thing I should say is, you hear it's eerily quiet. There's no traffic. This road's usually busy. It's getting serious now in the hospital. Let's open some parcels. Let's have some fun, I suppose. Come on. Our dead office chair is about to donate a wheel to the stand. Ian's just from the university has just brought some really cool stuff. Got some connectors. But the key thing are these bellows. We've got these lovely bellows. These are 3D printed, would you believe it? Just amazing, remarkable. And then we've got aluminium end discs, which they'll fit to. So you might be thinking, why are we going to build a ventilator with the bellows inside it if we're not sure where we're going to obtain the bellows from? In fact, we did have a local company set up to injection mold these for us. For the purpose of designing the ventilator, of course, we had the 3D printed ones made by Hans at the university, the professor of engineering. And at the same time, he also asked friends of his at a company that make undersea pipeline equipment to just consider making us a metal bellows. This is a stainless steel bellows. It's been set up to fit into our ventilator pretty much. And as you can see, it does compress and function as a bellows. In the future, I may build something using this just to see if it could work. You may be thinking, well, that's metal, it'll fatigue and crack after a few hundred cycles, but actually no, this is guaranteed for several million cycles, and it was very expensive. In the early 1950s, ventilators did actually contain automotive and bicycle parts. I've already shown you one that contained a 3-speed gearbox. So if you're in that frame of mind, one bellows that could be repurposed are these. These are steering rack gaiters, and they're readily available. They're found in all cars in the steering system. And this one displaces around 250 mils. So you can imagine perhaps 4 of these linked together in a ventilator, acting in parallel, instead of the single dedicated bellows. Plates are on now that the university have given us. Now the bellows will fit over these. Where's my jig? We're on a very low rate at the minute. In, hold, 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 exhale.
The vaccine programme was phenomenal. Somebody said to me, I'm not having the vaccine, you don't know what's in it. I said, yes you do, it's written on the box. Most of us in the company have been vaccinated for everything. You know, when you go for a vaccine and they ask you if you're allergic to mouse brains, you know you're pushing the envelope. So we're used to vaccinations, so there was no problem with people being vaccinated here. Nobody hesitated at all. As soon as they could have the vaccines, they would. I'd like to say it was unprecedented, but I'm not sure it was. I think we've been through pandemics before. We know what happens. We've run programmes in the UK on pandemic preparedness. I'm not sure that all the lessons were learnt properly, but you know, hopefully next time, and there will be a next time. That, I think, is the only thing that is sure about this.
Hopefully we get some more warning at least.
Well, that would be nice, yeah.
Yeah.
But
that's British understatement for American viewers.
Yeah.
Yes.
When the bellows moves back, air is drawn in through this one-way valve here, along with any oxygen that you may supply to it. And one reason we went for this type of design was that it doesn't depend on having any pressurized oxygen. When the bellows moves forward, this valve shuts, so gas moves through this one-way valve along the inspiration hose, this one, to the patient's lungs. It then holds it there, and then the gas is released through the expiration hose, the exhale hose, and it runs along here and out through this gas-powered thumb. You remember in the earlier diagrams we had an imaginary thumb which pressed on the exhale hose, and when it was time to release gas from the lungs, or let the patient breathe out in other words, the thumb was taken off the hose. Well, this is what this does. And the way it works is, when we're giving gas to the lungs, we want this to be closed, so the pressure of the gas going to the lungs is transmitted along this tube onto this silicone diaphragm, pushing it down over the hole. And when the bellows is moving back, and we're releasing the pressure, and we want the patient to breathe out, this pressure drops, and the diaphragm lifts up. So our imaginary thumb is then released, and gas moves out through our PEEP valve, which provides that little bit of back pressure to stop those alveoli completely collapsing down. This part has been made on a resin 3D printer. We came up with many designs for diaphragm valves, PEEP valves, and even both combined. Some made by us, some made by Hans and his team. And this is the one that finally worked, with a silicone diaphragm. How on earth do you make the flexible silicone diaphragm in here? Well, I'll show you. This was designed to be taken apart easily for sterilization. It could be made in metal or plastic, and the diaphragm is made of silicone rubber. We did look at commercially available diaphragms. One was from a classic car fuel pressure regulator made in Italy, and this was another contender, but in the end we decided to make our own. Let's make a diaphragm. So here's our 3D printed resin mold. The silicone comes as this two-part mix. Now we wait for it to cure. And there you have it, a silicone diaphragm. PEEP valves. You couldn't get hold of them at all during COVID. The university came up with this one, and if you take it apart, you can see it has all the required elements. It has the large spring, and then it has the little plunger on the inside with the much smaller spring on top of it. We now need to test this on our test lung. So, did we finish it in 10 days? Well, before we find out, let's take a trip to London to see one of the other groups building a ventilator around that time. This is Paddington Station, designed by Isambard Kingdom Brunel. You know, with a name like that, he's going to do something impressive with his life. A quick drive through London and we're nearly there. Here's the office of someone else with a long, impressive name. So I'm expecting great things here. As every guitarist knows, you can never have too many effects pedals.
March 15th, Jakob contacted our head of department. He sent out an email saying, does anybody know how to build a ventilator? And I said I'd give it a go. And so we got together and had a chat, and that's where it all started. So I was already on the project when the number was announced. He knew all about ventilators, and he might be modest about this, but as clinicians go, he's incredibly techie. So it was the perfect collaborator for me as an engineer, because he could actually communicate with me about engineering. And the first question I asked him was, what is a ventilator? Like, what does it do? And he described all these different modes of ventilations and all the different things that it needs to do, and I started to break it down.
On this fairly typical control screen, we've got the modes of ventilation, which all have shortened, abbreviated names. We've got the pressure of gas, we have the volume of each breath, here set to 580 mils. We have an oxygen control, set here to 55% oxygen. And there's also a timing element to it. We've got a setting here of 12 breaths per minute to be delivered to this patient.
Once we managed to break it down to those simple ideas, then I started thinking about how we could do it, and then realised we didn't have any of the bits we needed to do that.
So 14-year-old in school that thinks they might want to build medical equipment, what would your advice be to them?
So for the medical equipment side of things, the the expertise you need is the same as if you were building cars or motorbikes, which is how I got into it. It's physics, mathematics are the key principles. Originally I didn't want to go to university, I was going to be a rock star, that was the plan. So when I was 18 I finished my A-levels and I went to music college and worked as a musician for a couple of years. And I used to ride around Surrey on a motorbike with a guitar on my back teaching guitar. And the motorbikes kept breaking down and I kept having to fix them, and that kind of led me to mechanical engineering. Did you have any funding? Did anyone formally ask you to build this, or did you just get stuck in? Just got stuck in response to Jakob's email. We just kind of got onto it. The department were very supportive and they basically gave me a little bit of money to work with. And we requested funding, we applied for some funding, but we weren't successful with any of those applications, so we did it on a dime. From the start, it was almost, can we build it out of parts that I already have in my lab? Because even then, things that were in the UK, delivery was taking a fortnight. Did you find people you knew or even barely knew suddenly helped you? You know, all the red tape disappeared? Yeah, there was a lot of support. Within a couple of days of starting the project, actually, the number of emails for support got a bit overwhelming, and I was like, I have to be in the lab working on things. I don't actually have time to answer these emails. At times, it was very important to have the extra help, particularly for some of those components that I didn't have. We had a kind offer from a professor in mechanical engineering, and he just said, go and raid my lab for whatever you need. He worked in robotics, so they used a lot of pneumatics already. So yeah, things like that. Everything was a lot easier than under normal circumstances, and it was a lovely experience. So the building presumably was almost empty? Yeah, entirely empty, yeah. We got our food from Deliveroo, which thankfully was still running, but they'd kind of drop it on the steps and then we'd go and pick it up. Did you have any kind of impressive looking permit or letter from the Queen or anything to say this man is important and he must be allowed to do his work? Yeah, I did. We all got letters from the president of the college, which I would carry with me on my bicycle on the way in every day. Unfortunately, no one ever asked me for it, so I didn't get to use it, which was... But you were expecting roadblocks or something along those lines? Yeah, and instead it was just really nice riding to work because there was no one else around, so I just had the freedom of the roads. It was a little surreal. By 3 weeks in, we had a fully operating prototype that was built. I think our attitude was, there are people who've built simpler bag squeezer type devices. That will have to do for a few weeks at least, whilst we get our more advanced version nailed down. It can do effectively everything that an intensive care ventilator needs to do for 90% of patients or so. You're trying to do that with relatively unsophisticated parts? Yeah, and they're the simplest parts. Used in factories and things? Yeah, in fact, you often see them on cisterns. If you look up above the cistern, there's often this valve, and that's exactly the same thing. It's an on-off switch. It's open or it's closed.
A solenoid valve is a valve that's opened or closed by a magnet that's powered by electricity. So you can see one being used here. When you connect the battery, the valve opens. You can actually make one. In fact, you probably made something like this in school. You just need a metal tube, which here has been made from a biro. We put some cardboard on the ends, and then we wrap several hundred turns of wire around it. If you pass a current through the wire, look what happens. We can use this principle to open and close a valve, a solenoid valve.
And it's electronically controlled.
And yeah, you send just a simple electronic signal, so you don't have to regulate. There's no complex control around that, so it makes the whole thing a lot more simple.
So in terms of ramping up production, it's made in large numbers?
Yeah, and we spoke to several suppliers, and they didn't have any of the valves that normal ventilators used, but they had plenty of these valves because... That's the key point, really, isn't it? Yeah. Yeah, we found a couple of very helpful people who helped out, like with the valves that went in here. There was a very helpful sales guy at the company, and that really helped part of that whole thing of people being generous.
So modern intensive care unit ventilators certainly nowadays have touch screens and things. I mean, one thing I was thinking about was like, where would you even get 30,000 touch screens of the same design? from?
Yeah, we designed it so that the user interface was simple. We broke it down to like what are the minimum level of complexity that you need. So we designed it with a touchscreen in mind, but it could be reduced to a series of knobs and dials. So most ventilators have a series of different operating modes, which all have these confusing 3-letter abbreviations, and they seem to differ in what they actually do between different ventilator manufacturers. So we just were like, that is not a practical thing to do at all. What does a ventilator need to do? We basically gave it that one mode that could do that thing it needed to do.
If you ask a group of people if they'd like some free ventilators, what specification would they need? It seems to me that if they're used to using Rolls-Royce ventilators, then that's what they're going to ask for. Because if you're giving people stuff for free, then they'll want all the bells and whistles.
We're never going to achieve all of the bells and whistles, and they already exist because those ICU ventilators exist already. So we kind of went for some bells and some whistles, effectively.
The important ones.
Exactly, yeah. And actually even something like the spontaneous breathing or the ability to maintain pressure whilst the secretions are suctioned, which were two of the main things that a lot of the existing ventilators or a lot of the proposed designs fell down on. We were lucky because Jakob was like, you're going to need to be able to deal with these things fairly early on, and so we kind of built that into the design.
Did you sleep much for the first week?
Very little. It was 14-hour days every day. So yeah, it was a hectic time.
But was it strangely fun?
It was suddenly being like full on, just me and one other engineer, just like, what can we do? Writing the software, putting the bits of pneumatics together. It was strangely exhilarating, and you know, when we had all those pandemic phone calls and Zoom calls that everybody had, everybody else was like talking about sourdough.
Joseph, in 90 seconds, will now tell us how his ventilator works.
We have these 4 big green things here, which are valves. They're very simple valves that are either open or they're closed. And we have 2 pressure sensors. Because we just use these simple on-off, open-closed valves, we have to store up each breath in advance and then deliver that breath to the patient. And so that's what this container on the side is here. We call it a reservoir. We do that by basically opening first the oxygen valve into the reservoir.
Yeah, okay.
Then we fill it with the right amount of air into the reservoir. And we're monitoring the pressure inside the reservoir as we fill it up. And when we know that we're at the right pressure, which will give the right volume of breath, then we close the valves and we're ready to now deliver the breath to the patient. We then open this valve here, and then the air-oxygen mix will move from this reservoir through into here, and then across this valve, and then out here, and this would be connected to the patient.
Now remember, you couldn't get flow sensors that are normally found in ventilators. So what was their method of getting around this problem?
2 of the missing components that would be in normal ventilators are flow sensors. So the flow sensor records how much air-oxygen mixture is being delivered to the patient. And the clinician will want to decide an amount per breath, so say 400 milliliters. So we can measure that rather than using a flow sensor by using our 2 pressure sensors and the pressure drop, the pressure difference upstream of the valve on this side and downstream of the valve on this side.
This is actually very clever because if you remember, you can measure flow by measuring the pressure drop across a slight restriction in the pipework. In his case, they're using the valve itself as the slight restriction, and so they made their own flow sensor in effect. This valve opened to let the patient breathe out through the wider tube here. It then closed at just the right moment by accurately guessing the pressure inside the lungs, leaving a little bit of back pressure, and that eliminated the need for a separate PEEP valve.
So once you built a reasonably good working version, did you submit it for testing by the MHRA?
Yeah, we spoke with the government office and we had a phone call with them, threw together a quick PowerPoint, and we're put on a shirt and was on this call, and then actually about halfway through my computer crashed. So I could still hear the call, but my slides died entirely. They decided not to go ahead with our design. It was a little too junior at that point, possibly. If we'd spoken to them 4 days later, maybe they would have taken it on. But none of the ones they took on really actually worked out in the end, as I understand it anyway. So we actually submitted for the FDA, the emergency use authorization, and we put together, it was hundreds and hundreds of pages of documentation, sent it off to them, and then about a year later they were like, oh, we don't need any more ventilators.
You didn't have to send it to America and queue up and wait for a government body to test it.
Yeah, we do the testing, we send them the evidence, and they judge whether or not that evidence showed that it could work on
thousands of ventilators within weeks and not months, you're going to have to devise a localized testing system, aren't you?
You know, there was a big shortage of test lungs and bits of equipment for doing testing. If the government had got together and said, okay, there's 1,000 groups building ventilators across the country, let's choose the best 20 and send them a test lung and a test system, do their own testing, send us the results, that would, I think, have been, in hindsight, a much more efficient route.
If we hadn't suppressed the peak by using lockdowns and other treatments like CPAP had not been as effective as they turned out to be, how on earth, with a group of designs all queuing up for one testing body, would we have had 30,000 ventilators ready in 8 weeks?
Yeah.
I mean, there were no ventilators ready by 8 weeks.
No.
Let alone 30,000 of them.
We had a lucky escape.
Did we have a lucky escape? Well, let's have a look at what actually happened in the end. Mathematical modelling at the beginning of March 2020 suggested that in the worst-case scenario, the UK would need 90,000 ventilators, although this was revised downwards later on. In the event, the peak of the first wave occurred in mid-April, 5 weeks after the call, not 8. At that point, 10,900 ventilators were available, and nearly 3,000 of them remained unused. However, if 90,000, or indeed only 30,000, had been needed at that time, and other treatments such as CPAP hadn't worked, there would definitely not have been enough available. So on balance, we probably were very lucky. It's worth noting that as COVID progressed, other treatments such as CPAP really came into their own and prevented a lot of people needing formal lung ventilation on ICU. CPAP feels a bit like sticking your head out of a car window at speed, in that the air is under slight pressure as you breathe in, and then as you breathe out, you're breathing out against that same pressure.
I've been editing this documentary for weeks, and for all that time I've been trying to think of a good way to discuss the sharp spike that occurred in COVID cases. And then I thought, well, what about considering the Bitcoin price in late 2017? Don't worry, this is a fake. So if we look at this screen here, all will be revealed.
So for a couple of years, the Bitcoin price was a couple of $100. Nobody cared. It was a kind of geek hobby. And then bam, all of a sudden, 2017 August, everyone takes notice, including the press. $4,000, just like that. Well, it had been running for years before anyone noticed it. Now we carry on a few months, just a couple of months, look what happens. Oh, it spikes up. Now the curve is going up almost vertically. So what does that mean? Well, how high is it going to go? Well, nobody really knows, but clearly it can't go up forever because it would absorb all the money on the planet. And it's the same with COVID virus. It would infect everybody and there'd be nobody left to infect. What we can say, though, is that once it starts going vertical, then very soon after that, you'll reach the peak, which is exactly what happened. It came down again. So if this was COVID, what could you say? Well, once the number of cases starts shooting up almost vertically, you can say there's around some point soon after this yellow line, you'll reach the peak. So you know when the peak's going to be pretty accurately within a week or two, but you don't know how high it's going to go. Let's go and talk to Hans now at the Engineering School of Swansea University.
My name is Johan Siens. Everybody calls me Hans.
So I had a random phone call from somebody in the local government, and that's how I ended up doing it. So
Yes.
I remember rushing around to your house with a partially disassembled ventilator.
Yeah. Certainly I learned a lot about a ventilator in that afternoon, about its basic functioning from a mechanical point of view. Naturally software that was completely with you and others. It certainly it was a very intensive period. I remember we had early starts and late finish. We worked through the weekends. And the amazing thing was the team effort. Everybody pitched in, and yes, we produced quite a number of parts. Our colleagues from the workshop, they came in evenings and weekends to manufacture those on typically 24-hour notice. And they were absolutely incredible, and the professionalism and the dedication to get the prototype parts done.
Nick had the idea of making a kind of Meccano set of ventilator gas pathways, and then Hans at the university made the whole thing for us in stainless steel. You can see we have hub units into which the connectors are screwed, and some of them are blanking plugs, so you can design any configuration you want really quickly from this basic kit of parts, rather than making complicated one-off assemblies.
For the purpose of developing the prototypes, you managed to 3D print us some what looked like green rubber bellows.
Yes, we were quite fortunate. Again, a long time ago when we set up this campus, we thought, what is forward-looking technology and so on. And this printer, it's got multiple features in there. It allows large volume printing. And another feature is multi-material printing. And the one which stood out then was the soft polymer printing. Again, it was a challenge. I remember we did 2 or 3 failed trials of it. Although we had an existing bellow, we measured it down to the 1/10 of a millimeter. This material behaved differently, and it need different wall thicknesses, radii in the corners and so on, to be able to actually do the job.
Sent the video last night, sent it at 5 a.m, so still haven't had much sleep. It's very early in the morning, and we've just finished this in 10 days. So here I'm making a video presentation to the guys that challenged me to build this in the first place in 10 days. This machine will do this, because it's designed for this particular group of patients. So I'm filming it on my phone at the same time.
I'll just get this video.
The average mean oxygen consumption must be no more than 3 litres per minute. And then here I'm giving a point-by-point run-through, comparing it to the MHRA guidelines. It is a 3-year project, but we've just done it in 10 days. So there you go.
We need to mention the version 2 machine here. We were working on a larger screen. We're improving the gas pathways for removability for sterilization, so we tried a vertical design with enclosing clear panels, a horizontal design which had an expiratory lower module that would unplug as a complete unit for cleaning, and in the end we settled on the vertical design seen here in all its glory. A lot of people have asked how we made the acrylic cover. Surely we couldn't do that without specialist equipment. Well, we did. It was a requirement that the machine be waterproofed, so we enclosed it. To do this, you have to make a wooden model of your ventilator, and it has to be a perfect copy of the real thing. Nick cut out about 15 of these cross sections and glued them all together, which took ages to make this model. Then, using heat guns, we clamped the acrylic in place and slowly softened it where it needed to be bent. If you're very patient, it just starts to go soft, and then you have to quickly clamp it into the new position and let it cool down. So this is the moment of truth.
Okay, go on then, go for it. Look at that. Not bad.
And here it is, fitted onto the prototype version 2 machine. You can see it fits absolutely perfectly. You can also see the mechanicals now are all metal in the drive unit. There are now only 2 guide rods, and it's been simplified in that regard. These buttons, by the way, all come from arcade games and are readily available. The bellows unit now also easily comes out through the end for cleaning and sterilization. There are also 4 panels here which slide out downwards. This means this valve unit can come out and be cleaned. The valve can be changed and put back together. And the same with this one. And the same with the expiratory thumb device. We designed it like this with these silicone link tubes here between the valves and the metal parts, because if the valves needed to be changed for a different design and they ended up being a little bit longer, for example, it wouldn't really be a problem. So let's remove this. And it just slides off as quickly as that. While these panels may look complex, in engineering terms they're not. This is a flat panel that's had material removed on one side. Any engineering company can do this. It's basic stuff. And the same goes for this panel. Then, if we hold these together, you can see how the structure of the machine would start to develop.
We've reached the point now where we need to go and talk to Jakob, I think. So back in 2020, you were a trainee in intensive care.
As a kind of ST6, as I was then, often the most experienced anaesthetist on site out of hours in a hospital.
Hang on a minute, what did he just say? What's an ST6? Well, nobody knows. I don't think any of the patients in our hospitals really know either. So to explain this, let's take a trip to Port Miriam.
I'm here in Port Miriam where the cult TV show The Prisoner was filmed. And if you remember, everyone who lived in the village had a number instead of a name. And the hero used to shout, "I'm not a number, I'm a free man."
I'm going to talk about this problem with the junior doctors I attacked with the water pistol earlier. So in the old days, you had a house officer, a senior house officer, which you could be for a few years, registrar, middle grade trainee, that you would be for a few years. And then eventually be a senior registrar and then a consultant. So it's pretty simple, and it was a sort of military rank type of system. Here's a photo of a ward round taken in the 1970s, and despite what you may think about uniforms and stereotypes, from the patient's point of view, it's pretty clear who the senior nurse is, who the consultant is, and who the junior doctors are. Nowadays, you have FY1 Foundation 1 doctors, FY2s or 345s, then they could be CT1-2 core trainees or ST1-2 speciality trainees, then ST345, 6 and 7s, and eventually they become a consultant. So when COVID hit, Jakob was at this point as an ST6. If you're a junior doctor and you feel as if you're just a number, well, I'm sorry, but you probably are. Anyway, let's go back to Jakob.
I got an email back from Joseph Sherwood. He felt there was something to offer. I've always had an interest in design and sort of looked through technical manuals, and whenever there was an opportunity to have a poke on the insides of one, always done that. And, you know, with how complex these devices are, there was no realistic way that they'd be able to rapidly scale up to the demand that potentially we were going to need with a true global pandemic. It was very apparent with just the scale and speed at which the pandemic was hitting, and the fact that, you know, intensive care capacity was rapidly being overwhelmed, that there was going to be a shortage of everything.
In late 2020, the National Audit Office produced a report stating that there were in fact enough ITU beds for those that needed them. I just wonder if you have any thoughts on that.
Yeah, I think there's no question that services were overwhelmed. I think that was one of the incredible things about the pandemic, is seeing how quickly and willingly people were willing to go kind of outside of their comfort zones in order to supplement, kind of, increase that IT capacity. We created at my hospital an entire second intensive care unit very, very rapidly. And I remember my first day going into the hot zone, as it were, and having a few extra doctors from cardiology who were very willing to kind of hear my kind of basic, 15-minute talk of how to structure kind of my documentation as I would go round. And actually it turned out several of them were very, very senior cardiology consultants, world-renowned experts in cardiology, but they were willing to kind of, just be part, one member of the team just to kind of enhance that capability. So who knows how, if you'd had an unlimited supply, how many extra beds you would have created and whether or not mattered, and staffing wasn't a limiting factor. But again, this was a global problem, not just the UK. It's about doing the basics well in that situation. It's a disaster, so it's disaster medicine. It's not potentially pursuing every minutiae that you would do with unlimited resources or with a quiet ICU. It's about doing the basics well and doing that for the most number of people that you could possibly do it for.
Did you find people jealously guarding their domains, or did that all loosen up?
I think by and large, for the majority of people, most people were very willing to think. There were a few holdouts of people that didn't want to muck in, and I'll remember those names the rest of my life. I think by and large, I think that was one of the positives. The kind of feeling of a kind of global scientific community coming together to try and tackle that problem was one of the good things that came out of the pandemic.
What would be the best way forward if you did have another pandemic and you genuinely had needed 30,000 machines in 8 weeks, and you had not managed to spread it out and delay the peak?
So I think there's a couple of things. The need for some sort of pandemic stockpile to meet that initial demand of both protective equipment, not just for intensive care, but for kind of the front of house and wider wards, and then probably a stockpile of rugged equipment that can withstand that kind of 10-20 year lag time between being needed. Maybe not one ventilator, for example, maybe a variety of things to make sure that there's something at least that can work, can rapidly be stood up.
What are your reflections now, looking back from 2023 on the whole thing?
Yeah, I mean, it was a pretty extraordinary time thinking about it. So, I think we had the sort of the initial meeting with Joseph. I think it was on a Thursday or Friday. 3 days later, he'd started working on it, and by day 5, we had something that looked relatively functional. At the same time, our intensive care had gone from a sort of potential with 1 or 2 patients being put onto it to suddenly being completely full.
Did you have a very grandiose letter that gave you permission, if there were roadblocks, to ride through them?
Yeah, I mean, I suppose that was I guess it's one of those things, thinking back, of kind of realising just how out of control potentially people were thinking it was gone, and the president of the college sending me a letter that I was potentially, with the idea being that were the military or police to start having roadblocks around London, that I would potentially be able to present that to allow me to carry on the work. And I think that gives a reflection of, that actually looked like sometimes that society itself was going to completely crumble. Lots of people were working on very simple mechanical bag squeezers, and I knew that probably wasn't going to work, and the pitch was that we would try and do something more sophisticated.
The Indian standard for emergency use ventilators, when it came out, seemed to incorporate literally everything on the shopping list, as if they ticked every single box. I just wondered if that's what you heard.
The Indian standard, when it came out, was very large. So, it, for example, incorporated things like a tidal volume of up to 2 litres, which is something you would never want to do clinically. And that's that kind of compromise of, if you're asking for everything, actually that's actually probably pushing the limit of even what a kind of fully sophisticated $70,000 ventilator would do. Then you're effectively asking for nothing, because no one's going to deliver that.
Yes, so you're setting the bar so high, you're not going to get given any ventilators.
Yeah, and I think that's always difficult with any kind of clinical device, even kind of outside of pandemic design, is actually what is your actual need versus what you would quite like.
Yes. So where are you now? At the time, back then, you were a senior trainee. So you are now trained.
Yeah, so I've been a consultant for 3 years now. So my 3rd year of being a fully fledged anaesthetic consultant.
Baptism of fire, really.
Yeah.
Looking back, our machine really was designed for an apocalypse. In the event, pressurized gas supplies to hospitals generally were maintained along with electrical power. In the end, the UK didn't run out of ventilators, and also oxygen-based therapies such as CPAP were found to be more useful for the vast majority of COVID patients as the medical knowledge of the condition improved.
Don't worry, we have top people working on this. Top people.
It would be nice to think there's a massive warehouse somewhere full of equipment for the next pandemic, but I'm not so sure. Where are all the team members now in 2024? Nick finished his boat and realized his childhood dream. John finished his hot rod and raced it on a beach famous in the 1920s for land speed record attempts. Meanwhile, Dave formed a gypsy jazz band, and he's going to play out the credits of this film for us now. Off you go, Dave.